And we're back. How are you guys doing? Welcome to another podcast. Yeah, I know. I've been gone for a while, but I've been up to some stuff, okay? Let's get to it. I'll sit down. Alright, so currently I'm in my apartment in Atlanta. I move out in a day, so this place is pretty bare. Let me show you guys really quick. So I got a guy printing right here. He'll be printing during this whole time, so if you hear any weird beeps or something, that'll be the printer, alright? This one might be a little long and probably boring, so if you're not interested, just click away now. Thanks. Alright, what does it mean to be an engineer? I wrote it on this piece of paper because, well, I threw all the rest of my paper away from moving out. Well, I didn't throw it away, but I didn't have any to start with. Man, I'm going to miss this view. It's going to be pretty weird. So, I want to get into this idea of what it is to be an engineer, but really quick, I kind of want to update you guys on what I've been up to, because I don't think I've checked in about maybe 8 months or so. And last time you heard me, I was talking about building robots that drove on tracks on the ceiling overhead. And so I did that in my apartment. It was pretty funny. I delivered a bag of wine to one of my friends during his party. And I actually got fire marshal and structural approval and approval from the school and from Aramark, the food service company. And I was able to install the robotic delivery system within an actual restaurant and have it autonomously deliver meals to people as they're sitting down at a table. Pretty weird, I know. It was a funny system. We did about 70 autonomous deliveries, and then I presented it on national TV through this program called the Inventure Prize. And it was a really badass thing. I gave a great presentation. I really think I gave it my all, but I lost, funny enough. But after that, COVID struck. I'm sure you know what COVID is. It kind of sucks. And I was initially going to go into a partnership with Aramark in order to get my robots in another dining location. But everything kind of fell through once the whole scenario happened with COVID. And so I kind of pivoted to something else, which we'll talk to later. First thing I want to talk to, what does it mean to be an engineer? Well, who am I? I just had my 21st birthday, and I graduated today from Georgia Institute of Technology to become a mechanical engineer. And so I think I got something to talk and I got some beans to spill about the whole engineering process and how to go about getting it. And so I came out with a 3.46 GPA. So take everything with a grain of salt. I'm not a 4.0 nerd, but I think nerds are pretty cool and definitely very helpful. So yeah, I'll talk about the new direction I'm going with my life. I've been planning it for 21 years, kind of like a heist. And yeah, we'll have fun talking into that. I'll talk about that hopefully more than I even talked about waiter, because you know from the past few podcasts I was going off about waiter all throughout Europe and even after that. Okay, so what does it mean to be an engineer? Well, first I want to talk about like what an education at like an engineering school looks like, what they teach you, and kind of if you're going to get your money's worth. I'm just saying this because I'm an out-of-state student, and so the normal in-state tuitions I think around like $2 to $3 grand a year, a semester, and out-of-state tuition is like 20 grand a year. And so I was able to graduate a year early in order to save some money and time. I graduated in 3 years in a summer, and in doing this, the whole thing cost, well, that's 6 semesters total, so probably all in all 150 grand Thanks mom and dad and grandpa and grandma. That's really how I can be here and exist, is to them so far. And I'm really trying to make use of what I've been given to bring some of my benefits to the world. Not to be too corny. Okay, so in specifics, what have I learned as an engineer? Well, I came in to Georgia Tech and I had taken AP Computer Science. I've taken AP Physics 1 and AP Physics 2, or AP A, B, and C. I got 5s on all those. And then I took Physics 1 in high school as well, and I got a 4 on it. And so I didn't get the transfer credit there. So at Georgia Tech, my first 2 years looked a lot like taking Physics 1 again, and then also taking linear equations, which is a math class. And so linear equations really gets into like learning about matrices, which is just multi-dimensions of numbers. Really, it kind of started out talking about two-dimensional and then comparing different arrays to each other and how to multiply them and take things like the determinant, and really I think it's something that's helpful in a lot of data analytics and also in a lot of autonomous computer softwares, almost as essential as like multivariable calculus is, which is what they taught me next after linear. And through there is definitely going into understanding like different dimensions of how to run calculus, and then getting the equations and solving them somewhat like we learned within linear algebra by having kind of the matrices determine a set of systems of equations. And then after that, the next math course that was really kind of the pinnacle of math so far, I think, was differential equations. That class was pretty tough. It was basically more with rate of change of systems and trying to understand how if you want the variable at the end, the output of an equation, how you rearrange the equation so you can put the output to the input and figure out the steps that you need to get in between. And so that is very important in doing things like computer science, especially with robotics, and then understanding how to get the system to normalize at a certain equilibrium. And so then through kind of the mechanical, mechanical on the aspects of like transfer of fluids and energy. And so that started off with thermodynamics. Through thermo, we learned about basically energy processes of how energy moves in the system. Really, it was analyzing the combustion process and getting the efficiencies of the material once they were combusted, and understanding also processes like how a refrigerator works, because you can't just make cold. You have to take the heat away. Pretty much is the aspect. And that is kind of what we've got into in fluids and heat transfer. 2 courses after that are among some of the most difficult and complex that I've ever seen. Fluids was basically how water moves on a surface or on a pipe, or in a pipe, or in a chamber or a box. Basically how fluid moves in a bunch of different scenarios. And in mapping this, the main thing you got to consider is like how the fluid interacts with its exterior surroundings, because the main thing that they'll teach you is the no-slip condition, which means that if you have a fluid and the reason why it doesn't all flatten up to the ground, but there's like that surface tension is also a factor of fluids. So you got to understand that. I feel like definitely a professor is definitely good for this, but I'm kind of trying to summarize everything, because something I really wanted to understand when pursuing engineering is like, well, what are the like specific aspects of what an engineer learns to be an engineer? And it's basically how the interactions with the real world occur, and really initially trying to generalize them in the greatest way possible. And so really trying to get simple equations to map out kind of the way that basic things happen, like how normal flow happens in a pipe. But there's a lot of conditions that occur where the normal case is almost never around because you're neglecting some degree of freedom. And so in order to first estimate it overall, you have to start with these kind of bigger equations where you leave room for some error. I don't know if it still records when the screen goes dark. Yeah, okay. And then, yeah, some other classes that were pretty interesting were the structural ones, really statics, which goes into how loads are transferred along points and like beams. And so if you push here, you're going to have a torque here, and you're also going to have a force here. And really getting the balance of forces and moments is a big thing that leads to some considerable challenges down the road when actually building things. And we really learn that a lot in deformable bodies, where they teach you really about a beam and how exactly it deflects with a load at a given point. And so if there's a point at a specific area that is given some downward force, or if there's a distributed load where it's like a big flat piece is all pushing down at the same time, and kind of understanding how the beam deflects due to this. And given those deflection conditions is how you then determine things in like machine design, which is the next course. Another difficult course where you kind of design your system to be functioning within the regions of deformation, and understanding that, okay, if your tool or if your system deforms in any way, you gotta make sure that it does not deform too much where it breaks, and you also have to make sure that it does not deform too continuously that it will break eventually after an extent of time. Or you also have to think about how to make it so that, okay, if it deforms within these regions all the time, then there's never going to be a failure in your system. And that's really how you want to define for. That's pretty much designing for infinite life is what they call it. And that's in almost every like high fidelity component in like cars and planes and really high functioning mechanical systems. Is everything in it is defined so that upon constant deformation that it experiences, it will always return to its base state, or it will be able to be flexed enough so it will not break in a considerable amount of time. And so sometimes they make it so that, okay, maybe after 20 years the system will break. Okay, we'll give them that. And so, because sometimes you do have to make compromises, and you can't always define for infinite life, because either your cost point is going to be too high, or the manufacturability of it is going to be too difficult. And then furthermore, as a mechanical engineer, of course, you have classes where you have to build stuff, and you have to bring your knowledge of how things move into the real world, because that's what a mechanical engineer does, is they bring this knowledge of how things work and apply them to very complex mechanical systems. And so really the first way of understanding how to apply it is through a class called Dynamics, at least, that kind of taught you how to bring your mathematical equations and kind of differential equations into how systems work in like aspects of velocity and kind of joining two types of movement to one another. So like if I and pulling a pulley here, something else over there lifts a certain amount based on the ratio of pulleys. Or I turn something here that has a lever arm this long, which then forces the gear all the way over there to spin at a different velocity. And so those are just kind of the methods of getting you into thinking about how to understand the knowledge of math and physics into the real world. And then you go on further to apply them in courses like 2110 and Capstone. 2110 is just the name of the course. It's basically a systems design course where you're given a problem and a goal, and you build a system that solves this problem or goal, and then you go into a competition that tests how well your system solves the problem or goal in comparison to other systems. And so our problem or goal was like we had to push a little block out of a region in front of us. We had to like push it out, and then we had to go to this position about 2 feet in front of us, and we had to put a ball into it, and we had to take some little gemstones out of the middle and bring it back into our zone. And we had to do this all with robotic actuation. And that's probably the thing that I applied the most within my capstone project, was understanding how to use this robotic actuation to fulfill a need or a given problem. And so really the way that you actuate it, there's a few different ways that really a lot of them revolve around motors. And so motors, just like how wheels spin, they can be controlled to tell you how many rotations you want out of the motor, how fast it rotates, basically those two variables. And then from there you can say, okay, well, this motor spins a screw that has a nut on it. And because it spins the screw, the nut rotates naturally on top, and it rotates up just because it's transferring the rotational motion into up and down vertical motion. And that's called an actuator. And that is really it's a pretty cool thing, just because it really allows mechanical systems to be intertwined with software, which is freaking awesome. And then of course there's servo motors, which actuate rotational motion and can also be geared to perform actions similar to the actuator, which can also be geared in other ways to perform other actions, such as making a gripper that moves parallel, kind of like a hand does. And then there's also pneumatic actuation, which is filling like a tube full of air or sucking the air out of it in order to do a binary out and in motion. And you can also do that same idea with fluids called hydraulics, and that's a pretty intense procedure that you can't really do too cheaply, but it allows for it to, instead of being binary, and allowing for there to be variables in between, so you can tell how far the piston actuates. But that's something that a motorized actuator can do fairly well and can be programmed to do by software. And so what does it mean to be an engineer? Well, I just told you a lot of the things that I learned through being an engineer at Tech. And so mainly the culmination of all this engineering is expressed through their Capstone Design program. And so their Capstone Design program is basically, okay, use all the knowledge you have, present to us a problem, and then solve that problem with your engineering capabilities. So you have to design the system and understand what means of actuation or improvement you're going to give to the system in order to allow it to function to solve the problem that you prescribed. And so for my Capstone Design project, I tackled the idea of drone delivery with a really great team. I had 5 teammates, and the problem we try to solve is automating the procedures of package loading and unloading, as well as battery loading and unloading. So basically, the drone can operate completely by itself and kind of fly around, get a package from here, get a new battery, bring the package over here, get a new battery, and kind of continue on that whole process. And so we definitely ran into some issues because it's a very complex system that we have to design to do this. Really, so we made a repository that had a shelf full of boxes, and the idea was that the repository fed into a loading chamber of which filled a drone's cargo compartment. The cargo compartment basically lowered down into the chamber. It was then loaded up and then pulled back up into the drone. Okay, and so then that means we also had to have a landing pad, and so the drone's feet had to align perfectly with the landing pad when it landed. Very much not so the case of the current limitations of drone technology, but we said screw it, we'll take away that degree of freedom. And then we also had to have a battery swap chamber. And so this battery swap chamber basically had to store the dead batteries of the drone, pick it up, go into the drone's body, and well, first had to take the old battery out, put it into the charging shelves, which were shelves full of chambers that would be able to hold the batteries, and then we would take a new battery out that has been fully charged and put it back into the drone. And so to do this, we not only had to develop the actuators to raise the platform that performed this mechanical actuation up and down, but we also had to develop the mechanism and the electrical contacts that allowed the battery to snap into the drone and be locked in place during flight. And above all that, we designed the drone so that it could theoretically lift 6 pounds of cargo in a volume of about a cubic foot. And so that project's complete now. It was done with this drone, actually, and we built a very sizable portion of the system. We actually constructed all the components that were not necessarily mechanically actuated. So we built all the shelves, and the shelves were right here on the wall, right next to where you're sitting, if you're my computer. And the shelves were supposed to have a gantry on them that moved left and right and up and down. The gantry would be activated by stepper motors, kind of how a 3D printer works. And then we go take the package off the shelf through a mechanism that we also developed, and then kind of bring it down to another zone where it would deposit the package. So I definitely overestimated my engineering capability at the beginning, and the capability of like everyone on my team, because the system just came into a lot of problems when understanding how to fabricate everything with components that we did not necessarily have and that were not necessarily pre-designed. And so having to design a whole fleet of new systems from scratch is definitely difficult, especially because a lot of companies, once they develop the system that they do it, they don't normally like just say, okay, it's available to everyone now. They kind of keep it within themselves so that they can have the competitive power, which I think is definitely fair to them. It's cool and all. I don't know if it does bring the best overall benefit for the world, but that's an argument for another day. Okay. So then, what else have I learned? I've told you everything I've learned at Georgia Tech through mechanical engineering, but I have learned some things on my own through mechanical engineering with just some hobbies and interests of mine. Really, my hobbies and interests surround around always business propositions because they're the most exciting to me, and I am trained to be like an entrepreneur type dude. So the first thing I really developed from some of my knowledge at Tech was called the hidden smoke sleeve. You probably heard me talk about it before. The thing that held your jewel in your wrist, sure, cool thing. But I learned a lot about how to actuate motion through a spring and a rotational spool that then could serve a function. And then I also understand a lot about computer-aided design. If you want to be a mechanical engineer, you're going to have to love computer-aided design because it's going to be how you can make things in the world, right? That's what you want to do. Okay. So then, computer-aided design, I developed about 50 different renditions of this little thing that sat on your wrist and held the jewel sleeve, and then it sucked it back into the chamber and locked it in place for you. It was pretty cool. I went on, I sold about $200 worth of them, but then I realized it was kind of lame, and I got a cease and desist letter from Jewel Labs. So I kind of tapped out and was like, all right, I'm not going to push this forward if these guys are going to sue me for pushing it forward. The benefit's not really there. So then after that summer, I came back to tech, and I did a project called Booster Bracelet, where I learned a lot more about electromechanic, actually just electrical systems. And so Booster Bracelet was it was a bracelet that goes around your wrist that basically facilitates the function of the brick that like charges your phone in the wall. Okay, so like this top of the bracelet converted the power from the wall to power that you could use for your phone, and then on the latch mechanism, one side plugged into the wall and the other side was the lightning adapter that plugs into your phone. And I did this with the help of a good friend, Hunter Present, who was really kind of a good partner with me in this project. It was kind of fun working together because then we went further into I2P, so we got some grant money to keep developing it, and it was actually pretty interesting because like the circuit didn't exist to be small enough to convert the power from the wall into the power that we could use for the phone, so we actually built that circuit, and we were among one of the first people at Georgia Tech to use the new like laser engraving circuit board maker, which it was pretty intense. I really had to bug the people to get them to like let me use it, but it was fun overall. I made a lot of great friends and connections from that whole project, and then we presented it at the expo, and it actually worked. And it charged an iPad, albeit pretty slow and maybe not the best way a charger could function, but the little charger thing showed up, so we thought it was a pretty cool design, and we had the latch fit into the wrist, and we showed that it was actually smaller than the Apple design wall plug, which is, well, I definitely thought that was pretty freaking interesting. But yeah, we didn't win. Instead, this guy with drones won. He was making finger flyer boards. I don't know if they're around anymore, but they're basically a little tech deck drone. Yeah, okay, so I set my sights a little higher. I'm not sure what happened, but I think the computer glitched out or whatever. So I set my sights higher and I went for Waiter, and if you look up Waiter Systems, W8R Systems, you'll see what I was able to build. Robot drives in the ceiling, delivered food down, and I learned so much about more mechanical design and also integrating software into firmware, into hardware, and then into electromechanical movement. And I really loved that whole process because it got my wheels cranking on understanding how like you can really design some really freaking cool systems if you can bring all these things together, because they allow you to perform the normal functions that you can do normally. I don't know, like delivering food, sure, it's a little weird, but a robot drives in the ceiling, it comes from the sky right to your table. I think it was pretty cool, but I now understand, when further understanding, that didn't make sense. Okay, so an engineer, I understand that I've been doing the whole time what an engineer does, and that's solve problems. To be an engineer, it means to solve problems, right? You're taught every way. Okay, you're constantly handed problems. Everything they teach you, how do you solve this problem? This problem, what happens if this happens? All this. And they're the ones giving me the problems, you know? They're the ones always saying, oh no, you got 6 watermelons in your car. What temperature do you need for it to be outside, for all your watermelons to become frozen in 6 hours. Like they give you these problems so that when you're handed a bigger problem from someone else around that has a problem, then you can solve it, hopefully. You've been given as much information, or you've been taught how to learn how to get the information in order to solve that equation. So that's an engineer. Engineers solve problems. But solving problems is not the whole thing, I've realized. Solving problems isn't everything. Because sometimes you can solve a problem that doesn't need to be solved, or solve a problem that shouldn't be existent because there's a bigger problem causing a bunch of other problems, and your problem is just one problem created from that bigger one. Now, I said problems way too many times there, but I think you get what I'm saying. And I think the whole reason why I'm going early out of college of engineering, and why I've kind of lost my straight passion for learning in this engineering field, maybe didn't lose my passion necessarily, but more or less lost my passion for authority in telling me what problems to solve. Instead, I'd rather become something that I was taught back in high school through a program called Agents of Change. Shout out Dr. Agent, Mr. Valarezo. Really how to be an entrepreneur. And I know rise and grind, I'm an entrepreneur. It gets misconstrued a lot, but I think really it's because of the gravity at which it can bring positiveness. I think an entrepreneur is not necessarily the one who solves the problems, but he's the ones who finds the problems that are worth solving. And God, that's it, right? You gotta be finding the problems, or else the whole idea of what an engineer does is meaningless. You're just solving BS problems, you know? And I really think finding the problems or finding the questions, shout out to another book, or Hitchhiker's Guide. A lot of people talk about how questions can sometimes even be more important than the answers. And I think an entrepreneur is the one who asks the questions to the people that he wants to find how to solve their problems. And so through being involved in the Inventureprise and now CreateX, I have been working a lot to understand how I can apply my high level knowledge of electromechanical systems and software development, at least in the C++ level, talking directly to robots, how I can apply that in building something that solves a true problem. And I think that's the direction I'm heading right now. It is tough because you always come in with an idea of your end goal of, okay, obviously, if the world could work like that, that would be freaking amazing. But that's not just going to happen out of thin air because prices don't line up. It costs too much to do it. It's not bringing a benefit. The people that are going to benefit from it aren't going to buy it initially because the stakes are too high and the jump's too big. And so that's really a challenge of being an entrepreneur, is that sometimes you really have to it's not really a challenge or something, it's more of a puzzle. You really have to figure out how you can place the pieces of the puzzle in order to make the whole picture of what you want in the world to be like. And I think, alright, so my puzzle is how we can get drone delivery to happen for people in cities and suburban environments and rural areas. Basically, drone delivery in order to allow for rapid speed and also to allow for individuals to start shipping out their own items rapidly instead of, I don't know, just the way the whole mail system works. I find it truly annoying and aggravating, and I just think that with a system that can transport items autonomously and quickly will extremely grease the gears of how the human society functions, speed up progress, and in doing so give a lot more people accessibility to more tools in a quicker time period. And that's just something that I found that I could get behind the most, because it definitely aligns with what I find exciting, being drones and just robotic systems. And I don't know, I'm a sucker for robots, okay? What do you want me to say? And so in doing so, now I have to solve the puzzle of how to get there. And I really think sometimes you have to forget about the picture of the end puzzle, and you have to first start with the initial puzzle pieces. And you really have to initially start by talking to people and learning what challenges they have and what benefits you can bring to them. And in doing so, I enter into Capstone. I myself formed a company, Hive. Hive Technologies or Deliveries. I don't know what it's really going to be called, but Hive. And then from there, I commissioned, or I became the sponsor for the group of engineers who worked on the Capstone project with me. And so sponsors are people like John Deere or Caterpillar or like Ford, or someone that needs needs a mechanical system to be developed for their company. And they're looking for interns or people that they could then hire in the future. And so that's essentially what I became. I was one of those companies. And I was able to do that by getting a grant from CreateX. And so I kind of merged the two fields together. CreateX is like entrepreneurial at Georgia Tech, startup accelerator. Really great team, love the guys there. Really been helpful to me, and especially in designing the whole overall system of drone delivery, and then looking at it from the other side, saying, wait, you can't get there because you can't develop everything, and your system is not going to be adopted immediately. So what is some product that you can build initially that intertwines the idea of drone delivery into something that currently exists that brings benefit to some subgroup of people, targeting a niche market, which is pretty common base in startup accelerators or whatever. And so we thought all cumulatively, me and my team, me, Paige, Carla, are the three that are going to carry on. And Paige and I really were doing a lot of the big thinking about, okay, let's start talking to people. So we talked to some commercial drone flyers that like film stuff, and they're like, I don't really have that many problems. It'd be nice if my batteries last longer, but that's a problem for some extreme tech developers that are highly centered in battery development and manufacturing, which is like light years ahead of us, at least in my conceptual knowledge of battery manufacturing. And so then we're like, okay, can't go that direction. All right, let's think about, because we're also building a repository, what if we built a repository for apartment buildings to manage their packages automatically? Well, what's on the market? Well, there's a bunch of shelves where the delivery guy goes, puts the package in, delivery person comes in and takes the package out. Okay, it works, it's cheap, it doesn't really have that many problems, but if a robot was doing everything, it'd be cool, it'd allow for more space and more security, but it'd be a little expensive. And so we went and talked out to a bunch of places. They kind of told us that they had the same problem of constantly managing the packages, but there were better ways to solve it on the market that they currently were not investing in. So why the hell would they invest in something maybe 2 to 3 times more expensive that served a similar thing but with more detailed parts, more susceptible to failure? Yeah, can't go down that road either. So then we got thinking, okay, what would every drone need in the future, especially delivery drones? Well, their batteries, every time they fly somewhere, they either have to sit there and recharge, or someone's got to come up and take their battery out and put it back in. Well, hold on, there's already flight systems out there that are working to do autonomous maintenance inspection of like construction sites or power plants. Okay, what if we built a system that could integrate with a common drone on the market and swap its batteries out, making it not only an autonomous drone in a box, but also allow it to fly for 24-hour surveillance properties as well. And so that's the direction we're going now. That's the main overall idea, and we're probably going to do it for this drone. I got it. Surprised we actually won Capstone Design from the prototypes that we built of the system. I should be more hype about that. So woo! Yeah, it was pretty badass. We won the most engineering thing at Georgia Tech. Granted, it was during a pandemic, but who cares? It was fun and it was awesome. So yeah, we're going to be swapping out this drone's battery. Battery goes in and slides in like this. And so now I have to develop the end effector that comes down, pinches the drone's battery, takes it out, puts it in a chamber to charge, and put the new one in. And that's going to be, I think, pretty intricate. I have the base frame pretty much made. That was the printer finishing. That's things that just finished. We're actually mounting ball screws into the chamber that moves the platform that the drone lands on up and down, so that we can then from there service the drone within a known environment. And I think that's pretty crucial in how the overall system will work, and will make the design a lot simpler. So yeah, that's the direction we're going now. And the theory is, extrapolating the puzzle pieces, is we prove that we can do battery swapping with one drone that has a pinch battery on the market. And so we say, all right, hey, you got a drone, you want to increase its value to your customer, let us have one, and we'll build an end effector for you, so that our system now works with your drone, and it can facilitate this completely autonomous process without the customer needing to go out and buy an $100,000 monitoring system that's completely closed loop. We're going to close source. We're going to make more of an open source system that integrates flight software over here, drone creation from over here, and drone in a box from right here. And hopefully that will be able to sandwich together to create a system like this autonomous drone in a box, for an order of magnitude cheaper than everything that currently exists on the market. And that's 10x, baby. They're always saying something about 10x. That's 10x cheaper. Okay. So now you know all the pieces. Let's see. I already told you what I'm going to be working on for the next few days, few weeks. We got a big presentation August 20th with CreateX. That'll probably be online. So probably no one will be there, but I think we'll still be grinding, and then furthermore integrating our product with the software of the flight software company, who was actually the way that we got the confirmation for this. You remember I said, gotta talk to people? They were the ones who really kind of pulled the trigger and like, yes, we need this, let's go. I want to see it. And I really think that confirmation pretty much set me over the edge, being like, all right, it's build season. This is it. This is what we've been working for. This is the direction we got to go. And so now I'm working on that. And we have, so the rest of the people in the Capstone team, I definitely could not have taken them away from their jobs and life and priorities and everything, because overall this is just kind of a class for them. But I was able to steal one, maybe, for helping me at least part-time on a lot of the supply chain optimization work, which is essentially figuring out how to source all the components from the cheapest ways possible and then manufacture it the cheapest ways possible, which is actually kind of cool because it brings us profit overall, and profit's definitely something you got to have in a company. Let's see, and then we have Paige. She's more of like someone on the face of the company, building a lot of the front end of the website development, also a lot of managerial aspects in just figuring out how to correlate all of our connections with moving us forward in the sense of keeping us on track. And I think we definitely have a trajectory And the only way for us really to move forward now is if we have a product that works. So right now I'm standing at the base of a mountain, and there's a big mountain up there, and that's working prototype, and I have to get there soon. And so I think I will be able to develop some structure for my classless life. No pun intended, but yeah, I won't have any classes since I'm graduated. Yeah, I tried to get through this as fast as possible, but I think it took about 40 minutes. Too bad. You guys probably didn't watch the whole thing. Nope, no worries. I'm not here to take up most of your time. But now we're near the end. I did this during sunset. You guys are going to want to see it. I always have the best sunset from my balcony, which I'm leaving in a few days. Let's see. Yeah. It's a lot more beautiful with a better camera for sure. But yeah, I'm definitely going to be sad I'm missing this place, but I got a lab here at Tech with the professor. Big shout out to the professors of Capstone. They've helped me a lot along this journey, and I really hope I can deliver, you know? So, in conclusion, engineer solves problems, entrepreneur finds the problems to solve. I really want to be both, an entrepreneur-gear. That's probably the wrong word, but if someone thinks of another word, put it down in the comments. Smack that like button. All right, goodbye, guys.